Hi, welcome along. Little video on circular motion, completing our set of videos for ACP6. So we're going to imagine an object moving in a perfect circle, which of course I can't draw, moving along constant speed. So remembering speed is the scalar quantity, so the amount of distance it travels per second isn't changing. However, of course, its velocity is changing. So if we look at it in another location, the direction of the velocity has changed. Acceleration is rate of change of velocity. So all objects in circular motion have an acceleration, and it's an acceleration that constantly changes in direction, so that it's always accelerating towards the middle of the circle. So the velocity is always perpendicular to the acceleration. And if there's a acceleration towards the centre of the circle, there must be a force towards the centre of the circle as well, because F equals ma, so we're never going to have a force without an acceleration without a force. So it's not in equilibrium, it's got a constant acceleration. We can see also the acceleration is perpendicular to the direction of travel, and we know that work is Fs cos theta. So we can either say it never moves in the direction of the force, but because theta is 90 and cos 90 is 0, we never do that. That force never does any work. Relatively easy to say what the magnitude of the force is. We've got two equations. F equals m, the mass of the object, v, velocity, squared over r. But similarly, we've got F equals mr omega squared, where omega is the angular velocity, which is 2 pi f, which is the same as 2 pi divided by t. And that's a huge chunk of the circular motion already. It's not a huge topic, and I think I've covered the orbit stuff separately. So let's move on now to a couple of examples which just sort of make it slightly more complicated and interesting. So we won't do any maths on this one, because you know I like talking about the wall of death. So we've got our kind of motorbike here, got some handlebars, got our rider. Okay, I was going to go for them being more cheerful than that, but there you go, they're not being that cheerful. So they're riding out along the wall towards us. Must be a reaction force acting towards the centre of the circle. Must be a friction force acting up the wall. So the reason the reaction's there is because there must be a force pushing towards the centre of the circle to accelerate them in a circle. And that force is big enough to generate enough friction to stop them slipping down the wall. And those two components would make a resultant force, a total resultant force. I don't know why it's just me decided to ruin my diagram. With two components, the horizontal is the reaction force and the vertical is the frictional force. Where we can do some maths on this, if we continue the idea of objects kind of moving in a circle, we have what's called the classic banked track. So we might have a vehicle. We're looking at a vehicle coming towards us out of the page at you. And we generally imagine this without friction. So there are only two forces acting. Got the weight acting down. And we've got a normal reaction. So that would be perpendicular to the surface if there's no friction. And then vertically, we have an equilibrium. So the vertical component, RV, of the reaction must be equal to the weight going down mg. And then similarly, we must have a horizontal component of the reaction. And that's our centripetal force. That's what's driving us towards the centre of the circle. So RH equals mv squared over r. And these are, because these are components, we can say r squared by Pythagoras equals rh squared plus rv squared. So if we put rv, I'm just going to get it into green over here, you can see we've got a right angles triangle. The problem is, I always find this the hardest bit, we really want to get that angle up into that triangle. And that's not particularly easy, but we can extend that horizontal line, which is RH, and we should from there be able to see that angle there is also theta. So that angle there, if we draw a parallel line, is 90 minus theta there. So that angle there is theta. One of the best ways of sort of thinking about that is if you can imagine, sort of magically, we could make, I'm not going to use that pen, we could make the bank steeper. I said I wasn't going to use that pen, and I did. Whoa, it's all going wrong. If we could make the bank steeper, theta would get bigger, and if we rotated around, that would get bigger as well. So that must be the right angle. And then from that, we've now got, this right angle triangle. I'm going to redraw it out here. Here's the total reaction force. The vertical component is mg. The horizontal component is mv squared over r. So the hypotenuse is r. That's theta. So r, because it's the opposite angle, sine theta is equal to mv squared over r, and r cos theta is equal to mg. Or you can say, just need a tiny bit more space, tan theta is opposite mv squared over r divided by the adjacent, which is mg. So that gives us mv squared over mrg. And obviously the m's cancel and we get tan theta is v squared over rg. I think that will do us for circular motion. I hope you found that useful. Thank you very much.